everyone, I hope you're having a lovely weekend and that you're keeping safe and well. So this is our final lecture, and what we're going to be looking at are turning points and their nature. Okay, so first, to define a turning point of a graph or of a function. Okay, a turning point of a function is a point where f prime of x, so the derivative of f of x, is equal to 0. Now let's think about why that is for a second. Well, we know that the derivative of a function is the slope of the curve. Okay, so we're setting the slope to be equal to 0. And what that's going to give us is it will give us turning points. So, for example, if we look here in this graph, it's just a quick illustration. Here would be the maximum turning point and this would be the minimum point of the graph. And the turning point says where the slope of the curve is equal to 0. And at a turning point, the slope is going to be equal to 0 because if you think about it, if you were travelling up along here, okay, the slope wouldn't be equal to 0. Once you reach this point, we draw a line just tangent to it, it's a flat line. The slope of a flat line is equal to 0. And similarly here for the minimum. Okay, so to find the turning point of a function, it's where f prime of x, or where the derivative, is equal to 0. So what we want to do is we want to be able to find the turning points of a function and to state their nature. So whether they're a maximum or a minimum. And the method for doing this is we first set f prime of x be equal to 0. Okay, so we have to find the derivative of our function and set equal to 0, and we have to solve for x. After that then, we find the y values, the corresponding y values, that they will give us our turning points. To find if they're a maximum or a minimum turning point, we find the second derivative. So that means finding the derivative of the derivative. Okay, and sometimes this is written as f double prime of x. Okay, and if it is positive, then the turning point is a minimum. If it's negative, then it's a maximum. Okay, so this is our method. So let's look at an example. Okay, so for example, let's say we want to find the turning points of the function f of x, which is equal to 2x cubed minus 9x squared plus 12x plus 3. So we want to find their turning points and then we want to state their nature. Okay, so the first thing we want to do is find f prime of x, or to find the derivative of f of x. So here 3 times 2 is 6. We reduce the power by 1. 2 times minus 9 is minus 18, and we reduce the power by 1. And the derivative of plus 12x is plus 12. Okay, so that's the derivative of our function. Now we want to set that equal to 0 and solve for x. Okay, so we set 6x squared minus 18x plus 12 equal to 0. And we want to solve for x. Okay, so sorry, that's just a bit of, that's nothing there, that's just a bit of pen coming through from the last piece of paper. Okay, now to solve for x, we notice that this is a quadratic equation, okay, because the highest power of x is 2. Okay, and when we set it equal to 0, another way of thinking of this is that we're finding roots of the quadratic equation. Now, the roots of a quadratic equation will be the same whether it's this quadratic equation or if there's a constant that we can divide each term by, which there is, that one that will go evenly into each term. So first of all, we'll say that. So that is, if we could divide each term here by 6, for example, that'll make finding the roots a little bit easier. So here, that's x squared minus 3x plus 2 is equal to 0. So I divided each part by 6. And dividing by a constant each term in your quadratic doesn't change the roots. Okay, so we can find the roots of x squared minus 3x plus 2, and they'll be the same roots as this function up here. So one way of finding the roots that you may know about is by factorization. So factorizing this quadratic equation into its linear factors and setting them equal to 0. So in this case, it's going to be 2 times 1, a minus and a minus. Okay, and if you're not sure how to do that, go back and revise a bit of factorizing quadratic equations. Okay, and then we'll get that x minus 1 is equal to 0, or x minus 2 is equal to 0. So this means x is equal to 1 and x is equal to 2, just for solving for x in each part here. Okay, so now we need to find the corresponding y values for x being equal to 1 and x being equal to 2. So we go back to our original, go back to f of x. Okay, not f prime of x, just f of x, and substitute in x being equal to 1 and find your corresponding y value, and similar for x being equal to 2. So what we're looking for is f of 1, okay, where we substitute 1 in for x. Okay, so 1 cubed is 1, multiplied by 2 is 2. 1 squared is 1, multiplied by minus 9 is minus 9. We get plus 12 plus 3, which is equal to 8. Okay, so the first point that we have, x is equal to 1 and y is equal to 8. Now let's solve for f of 2. It's 2 times 2 cubed. And remember to substitute your number in brackets. Minus 9 times 2 squared plus 12 times 2 plus 3. So that's 2 times 2 cubed, which is 8, minus 9 times 4, plus 24 plus 3, which is plus 25. So we'll get 16 minus 36 plus 25. And that will, apologies, sorry, this is my mistake. 12 times 2 is 24, plus 3 is 27. That should be 27. Okay, and when we add them together, we'll get back 7. So the other point that we have is 2, 7. Okay, so these are our two turning points, but now we want to state their nature. So we want to see if they're maximum turning point or a minimum turning point. Okay, and the way to do that is to find the second derivative of f of x. So, and we call this f double prime of x. Okay, well remember that f prime of x, so the derivative of f of x was 6x squared minus 18x plus 12. And to find the second derivative, we differentiate the first derivative. So now differentiate this function. So we'll get 12x minus 18. Okay, so that's our f double prime of x. That's our second derivative. Now whether to find out if our point is a maximum or a minimum, we know that we found that x was equal to 1 and x was equal to 2 previously. Substitute these into f double prime of x. So here f double prime of 1 is 12 times 1 minus 18, which is equal to minus 6. And f double prime of 2 is 12 times 2 minus 18, which is equal to plus 6. Okay, and the sort of method for determining whether it's a minimum or a maximum is that if the second derivative of f of x is less than 0, then you have a maximum. And if f double prime of x is greater than 0, then you have a minimum. Okay, and think of less than 0. Another way of thinking of that is saying that it's negative. And greater than 0, another way of saying that is that it's positive. So when we substitute it in 1, corresponding to our 0.18, we get back a negative. Okay, so that means that the 0.18 is a maximum. And when we substitute it in 2 for the 0.27, we got that it was positive, or a positive number greater than 0. So our 0.27 is a minimum. Okay, so let's look at another example of that. Going through it again. So example 2, it's the same sort of method again. So let's say f of x is equal to minus x cubed plus 6x squared minus 9x minus 5. Okay, and we want to find the turning points of this function and state their nature. Okay, so f prime of x, the first thing we have to do is to differentiate. We'll get minus 3x squared plus 12x minus 9. Now we set that equal to 0 and solve for x. Okay, so minus 3x squared plus 12x minus 9 is equal to 0. Okay, but similarly to before, there's a number that will divide evenly into all of our terms, and that number is minus 3. So we're going to divide across by minus 3. Okay, and that'll give us x squared minus 4x plus 3 is equal to 0. We just divide each part by minus 3. And the reason as well, the reason I want to, I suppose, is the easiest case to solve quadratic equations is when our x squared term, where the coefficient of that is just 1. So where there's no number as such behind it, like minus 3. So where it's just x squared by itself. So that's why I've chosen to divide across by minus 3. It's because when I divide minus 3x squared divided by minus 3, I'll get back x squared. And minus 3 will go evenly into both of these as well. Okay, so we could factorise that. If we were to factorise that, we'd end up getting 3 times 1 minus x minus 1 is equal to 0, x minus 3 is equal to 0, so x is equal to 1 and x is equal to plus 3. Now, if you're not sure how to do the factorisation, there is something called the quadratic formula that you may have come across before, and that'll help us to solve the roots if we're not sure how to do it by factorisation, or if we can't do it by factorisation. Okay, so the formula, quadratic formula says, okay, so for a quadratic formula that is in the form ax squared plus bx plus c being equal to 0, the quadratic formula is minus b plus or minus the square root of b squared minus 4ac all over 2 times a. Okay, so for our particular question, okay, if we're not sure how to factorise, for our particular question we had x squared minus 4x plus 3 is equal to 0. So the a is our coefficient of the x squared. So here, the coefficient here, there's 1x squared, so a is equal to 1. B is the coefficient of x, which is minus 4 here. And c is our constant, which is just a plus 3. So once we've identified our a, b's and c's, we can just substitute them back into the formula to solve for x. Okay, so x is equal to minus b, which is minus 4, plus or minus the square root of minus 4 squared, minus 4 times ac, all over 2 times a. Okay, and that will give you 4 plus or minus the square root of 16 minus 12, which would be 4 over 2. X is equal to 4 plus or minus 2, because the square root of 4 is 2, over 2. And now to get our two roots, we'll let one of them be 4 plus 2 over 2 and the other one be 4 minus 2 over 2. So x is equal to 4 plus 2 over 2, which is 6 over 2, which is equal to 3. And x is equal to 4 minus 2 over 2, which is 2 over 2, which is equal to 1. So similarly to before, if we were to just factorise in the previous example, we get our roots to be x is equal to 3 and x is equal to 1. So now let's find our corresponding y values. So go back and find f of 1. Okay, so we go back to our function f of x. Okay, and in particular that's minus x cubed plus 6 times x squared minus 9 times 1 minus 5. That's minus 1 plus 6 minus 9 minus 5. Okay, which is equal to minus 9. So we have our first point, our first turning point, which is 1 minus 9. And when we substitute in 3 for x into f of x, get minus 3 cubed plus 6 times 3 squared minus 9 times 3 minus 5. Okay, so 3 cubed is 27, multiplied by minus is minus 27, plus 6 times 9 minus 27 minus 5. Okay, and when we work that out, we'll get back a minus 5. So we have another turning point, which is 3 comma minus 5. Now, we want to know which is our maximum and which is our minimum. So we're going to find the second derivative of our function. So in this case, f double prime of x, okay, is going to be minus 6x plus 12. So let's substitute in our x values for that. So f double prime of 1 is going to be minus 6 times 1 plus 12, which is equal to a plus 6. And f double prime of 3 will be minus 6 times 3 plus 12, which is minus 18 plus 12, which is equal to minus 6. And it's just coincidence that in both of our questions, examples that we've done here, that the f double prime of our x values turn out to be 6 and minus 6. It's not always going to be the case. When we know that 6 is a positive number, so it's greater than 0, and minus 6 is a negative number, so it's less than 0. So therefore our point 1 minus 9 is our minimum, and the point 3 minus 5 is our maximum. Okay, so there's how to get a function, find their turning points, and to state their nature. So let's see a couple of applied examples of this. Okay, so for example, here's an applied example. So s of t is equal to this function, and it gives the height in meters of an object after it is thrown vertically upward. When will the maximum height be reached? So if you even think of it in terms of a graph, okay, the way that this graph looks, because it's a negative at the start, the graph will look somewhat similar. It'll look upside down, almost like a sad face, sad mouth. Okay, and think about what we're doing. Well, we're throwing the object, and the object is going up and up and up, and the maximum height at which it'll be reached is there. Okay, so when it's, in other words, when it's stationary as well, there'd be a point where you throw it upwards that it'll just stay at the highest point for a split second and then come back down. Okay, so again, what we're going to do is we're going to find s prime of t and set it equal to 0 and solve for x. So S prime of t, so when we differentiate S, we get minus 9.8 times t plus 49. Okay, and we set that equal to 0. And notice that this is linear, okay, the highest power of t is 1, so we're just going to have one value for t. Okay, and t here in this particular question represents seconds. Okay, so we have minus 9.8t is equal to minus 49. So t is minus 49 divided by minus 9.8. So t is equal to 5. Because t is seconds in this question, t is equal to 5 seconds. Okay, so the maximum height will be reached at 5 seconds. So let's look at another example that's similar to your journal question. Okay, it'll be fairly similar to this, same sort of ideology behind it, the same method and so on. Next example is a researcher has the function y, which is equal to minus x squared plus 16x minus 65 for the number of impulses fired after a nerve has been stimulated. When will the maximum firing rate be reached? And just to note that y is the number of impulses per millisecond and x is the number of milliseconds since the nerve was stimulated. Okay, so let's differentiate. So it's written in terms of y, so we can say dy dx, okay, is minus 2x plus 16. Okay, and what we're going to do now again, similarly to before, is we'll set this equal to 0 and solve for x. So minus 2x plus 16 is equal to 0. So minus 2x is equal to minus 16. So x is minus 16 divided by minus 2. So x is equal to 8. We know that x is the number of milliseconds since the nerve was stimulated. So x is equal to 8 milliseconds. Okay, thanks guys.